Yes, alright, great. I figured to use the microphone, we'll pass along, hopefully without some weird noises. Alright, welcome everyone. Thanks for having us here today, and we're very pleased to be here all the way in Nijmegen. Let me grab my mouse and introduce the team real quick. My name is Elias. I was a bachelor student at the Vrije Universiteit once. I'm here together with Max, and I'm here together with Darian, and we are all under the supervision of Natalia, who is right there in the middle. And like I said, we come from Amsterdam, and we have all once been undergraduates in computer science under the supervision of Natalia. And today we're here to talk about the VU Rover and its many capsule project. So let's dive right in. This is the Rover, and it's a small-scale autonomous vehicle. Well, almost good there. It's a small-scale autonomous vehicle with some sensors and some motors, and it finds its origins in the NXP Cup, which is a global student racing competition that is centered around having a car, bringing it to a track you've never seen before, and racing it as fast as possible on this unseen track with your own hardware and software. I joined in 2020 when this project was already going on for many years, and hopefully you can see me there in the corner. Now, in my defense, it was COVID and the hairdressers were closed, so don't laugh at me. But when I joined, NXP wasn't so like things definitely were not smooth, and we had some problems with the software and the hardware that was provided to us by NXP. Like you can see here, it was very hard to see what's going on and what we could improve. And it actually caused quite some frustrations. So when Max joined the team in 2023, there has to be something done to improve this, right? So that is how ACE, the Autonomous Systems Engineering Lab at the VU, was born. And we started by building our own hardware and software from the ground up with everything that we had in mind that we thought was important for ourselves as students and to win the NXP Cup, of course. Yeah, we did this, like, all the aspects we did in-house, so from hardware and software and electronics, actually a major achievement to say so myself. This has all been done by Niels who is unfortunately not here, but he did a major job in getting the PCB and the power delivery board to work as perfectly as it does. This is all powered by the DevX Model A. It's a single board computer similar to the Raspberry Pi, works great for us, and it actually also powers our most essential piece of software called Rover D, which manages service pipeline execution. In the service design where we opted for, which we will come back later. This is controlled by Rover CTL, which runs on the laptop, which is used to also to send commands to the Rover, but also to receive data from the Rover, which is crucial, but I will show you in a bit. And for people from the Kubernetes world, this might ring a bell. Alright, so this is what it looks on your laptop. This is Rover CTL, and here you can already see our service-based architecture, right? Like we have some services enabled there, and hopefully it intuitively makes sense how this works. We have some image capture, we do pre-processing, take a capture from the webcam, and find some interesting heuristics. Then with the controller, we decide where to steer to, and our low-level actuator makes the driving actually happen. And that looks like this. If we started in ProCTL, you'll see it start driving right away. Very nice. But we didn't stop there, right? This doesn't win us races yet. Because we had to focus also much on modularity. We wanted to do A/B testing, we wanted to make sure, does this work, or does this work better, or does it not work at all? And maybe we want to add more sensors later on. So these services, which can be written in many languages, as Max will tell you soon, can be swapped in and out, like you see here. Now we add a distance service. We start a distance service, and now suddenly our rover has become distance aware. Great. All right, but what about the most, and I cannot stress enough, the most important feature of our rover? We want to be able to debug the rover and also to tune it lightly, right? Because if we don't know what is going on, what the camera sees, what decisions it's making, we cannot improve it also. So that's very important. We have, around this whole service-oriented framework, we have built a tightly integrated debugging framework, where we can see here, on the left you can see the camera feed. You can see it right now, the camera feed, and you can see, as important also, our live data being charted and plotted and being able to be tuned so that we can change the steering behavior of the car. Alright, that's great, and it also benefited us greatly in the speaker. Here you see that a bit of a higher speed. Like if we try to improve the cornering speeds, for example, we want to see how does it perform now. We want to see the charts, We want to be in a Formula One racing room, debating some nerdy details, and then say, okay, we need to actually increase the speed a bit.
So now maybe the question you've been waiting for, what does any of this actually have to do with education? So coming back to the Rover, we thought to ourselves, this package that we made actually is composed of a number of different topics across computer science. For example, we have the camera, which takes as inputs the environment, so we use computer vision algorithms, and there's opportunity there to study those more in depth. Since it's a real-time system, we have plenty of opportunity to reduce latency and make the system more energy efficient. Furthermore, as a robot, it is susceptible to hardware and software vulnerabilities, so analyzing it from a security perspective is also relevant. And since it's a physical thing, it would be very nice to understand things about properties about it physically in simulation and run our software in a simulated environment. And finally, we didn't just build one of these rovers, but in fact we made 20. And so thinking about them in a context in which they communicate together, like in the Internet of Things, is also very relevant. And these topics didn't come quite out of thin air, because at the VU we were fortunate to have a number of very dedicated professors that specialize in these areas. And we reached out to them and we asked whether they would like to take on their students in their final year capstone projects and do it in the context of ITiCSE, of our platform and hardware and software that we provided. So the idea is that the professor brings their expertise and their research questions, and we provide a lab with robots that students can engage in. And so what this helped us with is unlock a little bit of scale. At the Vrije Universiteit, we had a large influx of computer science applications, and one of the biggest challenges there is finding enough final year projects. And so we addressed this to a certain extent by creating a unified framework in hardware and software that then can be addressed in different ways, in different research questions, to different topics, and robotics happens to be one that is very adaptable to that. Now the key question, maybe you've also been waiting for, is this is quite challenging. So how did we address, or like the rover that we made and the software is all rather complex. How did we address the complexity? We documented as much as we could. So here, from a student's perspective, they can look at tutorials on getting started with it. They can take deep dives into the electronic components as well as the hardware and really learn about the software that we provide. The software that we provide is there to bootstrap and speed up their project. Of course, they have the ability to just use their own software and do kind of whatever they want. Of course, all the code is open source, so that is a learning platform as well. And we offer a number of languages to really get started with this quickly. So in the example case of a student wanting to use a new imaging algorithm in Python, they can use our templates to integrate it into the system rather quickly. And so now another question you might be wondering is, how did all of this go? So Darian here will tell you more about that.
So, hello everyone, and me and my team focused on researching different algorithms on how to pinpoint where the rover is indoors. So that really meant we couldn't use GPS. The first algorithm we focused on is wheel odometry, which basically takes an RPM value from the wheels, couples it together with the steering angle, and can precisely estimate where the rover is at any point in time. The second algorithm we focused on is visual odometry, which basically takes two consecutive frames, identifies features in those frames, and based on how those features move, it estimates where the rover is. You can think of this as a mouse moving on a table, and its movements are actually reflected in the cursor. The final algorithm we focused on is visual inertial odometry, which basically couples the estimations of the camera from the previous algorithm together with an inertial measurement unit in order to get a more accurate estimation. The inertial measurement unit is just a combination of accelerometers, gyroscopes, and magnetometers. So, you're all wondering, how did this framework actually help us? Most importantly, it allowed for concurrent development. This is just a depiction of a pipeline. We had the basic sensors to actually make the rover move, and we could simultaneously and iteratively develop our own algorithms. This also allowed us to swap in services that we didn't want, and also we could change the behavior of the rover. Finally, we were able to standardize the testing. As you can see on this illustration, we were able to put the QR code on the rover itself, and with the top-mounted steering camera, we were able to find the actual ground truth and compare the algorithms to it. So these three things really helped us, but every team benefited differently. All right.
to Darian. Good to know that Darian has been one of the 35 students so far who has been part of the ACE framework that has been organized by Natalia in the first place and on the data organization by Max and me. And this is something that we want to wrap up with, right? Because this is the take-home message that we want to bring across. This started as something that is inherently just fun. We did this because it was fun. I've been part of this since 2020 because I thought it was fun, and this actually grew into something that provided a perfect research platform for so many students in the field of robotics and racing. And yes, thank you all for being here. And you also are probably wondering, okay, but how does this connect back to the XP Cup? Glad you asked. We won the XP Cup in 2024, and we took home the prize, and we're very happy that we landed this way. Thank you.